Graphs are fascinating structures that play a crucial role in both mathematics and computer science. At their core, a graph is a collection of nodes or vertices connected by edges. Imagine a social network. Each person is a vertex, and the connections between them, friendships for example, are the edges. This simple representation can model complex relationships and interactions in various fields. Now, let's dive into the two main types of graphs: directed and undirected. In an undirected graph, the edges have no direction. If A is connected to B, then B is also connected to A. Think of it like a two-way street. Both cars can travel in either direction. On the other hand, directed graphs or digraphs have edges with a specific direction. If there's an edge from A to B, it doesn't mean B is connected back to A. Picture a one-way street. You can only go from A to B, not the other way around. This distinction is crucial when analyzing relationships, as it can change the dynamics of how we interpret the data. Next, let's explore homomorphic and isomorphic graphs. These concepts might sound complex, but they're quite intuitive once you break them down. Isomorphic graphs are essentially two graphs that are structurally the same, even if they look different. Imagine two different maps of the same city. They might use different symbols or colors, but they represent the same layout. In graph theory, if you can redraw one graph to look exactly like another by simply renaming the vertices, they are isomorphic. Homomorphic graphs, on the other hand, involve a mapping between two graphs that preserves their structure. If you think of a homomorphism as a function that translates one graph into another while keeping the connections intact, you're on the right track. This concept is particularly useful in computer science, especially in database theory and cryptography, where maintaining relationships while transforming data is essential. Understanding these graph concepts opens up a world of applications. For instance, in computer networks, graphs help model the connections between different devices, enabling efficient data routing. In social media, algorithms use graphs to analyze user interactions, recommending friends or content based on connections. In biology, graphs can represent relationships between species in an ecosystem, helping researchers understand biodiversity and species interactions. Graphs also play a pivotal role in optimization problems. For example, the shortest path problem, where you want to find the most efficient route between 2 points, can be solved using graph algorithms. This has real-world implications in logistics, transportation, and even urban planning. By grasping the fundamentals of graphs, directed versus undirected, isomorphic versus homomorphic, you're not just learning abstract concepts, you're gaining tools that can be applied in various fields. Whether you're analyzing data, optimizing routes, or modeling relationships, the principles of graph theory are invaluable. So, the next time you encounter a graph, remember that it's more than just lines and dots. It's a powerful representation of connections and relationships that shape our world.